The second half of this video asks you to use SPSS. So you might want to work on a different screen or device to do that, so you can see the slides at the same time. This is what we're covering in this video. The first half of the video we're going to talk about how to choose the right statistical test, and we won't actually be using SPSS to do that. There will be bookmarks so you can jump to any of these sections. And this might just be the start of your statistical understanding. This video won't be able to teach you everything about statistics. So just be aware that you will need to study statistics further. So let's talk about how we choose the right statistical test. This is the most common question we get in the Math Skills Centre. In order to choose the right test, we need quite a lot of information about the experimental setup. So we need a null hypothesis. So we need to be very clear what it is we're testing. We need to identify whether our experiment has a dependent and independent variables. And if it does, then specifically what measurements are those dependent and independent variables? And what type of data are they? We're talking about scale, ordinal, nominal here. Then we need to know whether the experiment had any repeats or paired data, or whether it was what we call independent data, and the number of levels. So that's quite a lot of terminology for you there already, but we're going to try to explain that along the way. Once we've got all this information, you can use your previous knowledge to choose the right statistical test, which is why practicing statistics makes it easier. Or if you're a beginner, there are flow diagrams or statistical choice test trees or tables which can help you. For this video, we're going to use one that the Math Skills Centre has made, but you can use any that are out there. If you just Google statistical choice test trees or something, you'll get a whole load of them if you press on images. So in this document, which is on the VLE, we explain what you need to make the choices. We've got this flow chart here, which we're going to go through with some examples. And because there is a lot of statistical terminology, then we've got definitions on the other page along with examples to try and remind you of what we're talking about when we ask you these questions to answer what way to go in this diagram. So first thing we need is a hypothesis. It's usual to write out two hypotheses. One's called the null hypothesis and one's called the alternative hypothesis or experimental hypothesis. And it's quite common to see them written out as H subscript 0 and H subscript 1. They're very similar, except the null hypothesis is like saying there's no difference, there's no correlation. In other words, there's nothing exciting going on. There's no significant differences. So here we've got an experiment where we're asking different sets of people to run on grass, tarmac or track, and then we're measuring their stride length. So our null hypothesis here is that there'll be no difference in stride length between people running on different surfaces. And the parts that I've put in bold here are the word difference, because that clarifies that we're looking for a difference opposed to a correlation. And then I've put in stride length. That's something we're measuring. And different surfaces, that's different study experimental situations, different groupings. The alternative hypothesis is the exact same, except it says that there will be a difference. I've put in another example here of a different study because we might be looking for a correlation or maybe an association between two things. Here we're measuring mood rating and we're also measuring people's perceived enjoyment of university. So the hypothesis helps you to pin down what it is you're measuring and how you're looking at that relationship. Is it a difference or an association? Once we've got that, we can then start to think about whether we've got any dependent or independent variables. You might have heard dependent and independent variables called different things. Statistics has a nasty habit of having lots of different terminology for the same thing. So a dependent might be called a response or an outcome, and an independent could be called predictors or factors. And some people try to identify what the dependent is by thinking about this. The dependent is changed or affected by the independent. So to make that clear what a dependent and independent is, we're going to look at some examples and pick out the dependent and independent. So here, as an example, we've got the experiment where we're asking different sets of people to run on grass, tarmac and track and measure their stride lengths. So what we're asking is there an effect of the surface on the stride length? In other words, is the stride length dependent on the surface? Therefore, stride length is our dependent variable, Stride length is our dependent variable, and the surface is the independent variable. If you want to have a go at identifying the dependent and independent variables, or whether there are independent or independent variables in these other 4 examples, you can stop the video now and you can have a think, or you might even want to write down the answers. Here are the answers. We've got the top one done already. The second one, we're looking at the difference between 2 colours of museum signs, and we're timing how long people spend reading the signs. So our hypothesis is that the colour of the sign affects the time people spend reading. So therefore the time that people spend reading is dependent on the colour of the sign. Therefore the time reading is dependent and the sign colour is our independent. When we come down to number 3, we're looking at an association between beer and nappies and whether they occur together in people's supermarket baskets. So we're just looking at different people's baskets and how often they occur together. In this case, we can't really say that buying beer causes someone to buy nappies, or buying nappies causes someone to buy beer, though you might argue differently. And therefore, we're just looking for an association, and we don't have a dependent or an independent here. We just have 2 variables, and you wouldn't really call either of them dependent or independent because there's no cause and effect. We've got another example here where we've got 2 variables. One's people's pet preferences. Let's just say we ask people whether they prefer cats, dogs or both, and then we ask them whether they are male or female. So the dependent here is the pet and the independent is the gender. And that's because we're hypothesizing that gender affects your pet preference. Therefore, your pet preference is dependent on the gender. So pet is dependent. And then number 5, you might have had some difficulty with, and that's absolutely fine. Because number 5 can be thought of in 2 different ways, depending on what your research question is and what your hypothesis is, which emphasizes why it's important to pin down that hypothesis at the start. So we can think of how happiness is related to a person's income as being no cause and effect. So we can think of it as we just want to see if there's an association, and we're not hypothesizing that one affects the others. In that case, we wouldn't have a dependent or independent. So it's fine if you got that answer. It's also fine if you were hypothesizing that income does have an effect on a person's happiness. In that case, the happiness would be dependent on the income, and the happiness would be our dependent. The income would be our independent. Now we've got that information, we need to think about these measures and what type of data they are. I've got a screenshot here from SPSS. You might remember, or you might be familiar with the variable view in the column measure, and you have to choose in SPSS whether your data is scale, ordinal or nominal. So nominal data, you can think of it like categorical data. It's a measurement that is put into a category. So gender is a really common categorical piece of type of data, which is nominal. Or treatment. So you might have method 1, method 2 teaching, and that's a category. Similar to that are ordinal data. So ordinal data is similar to nominal because it's categorical data. You're putting things into a category. But this time there's a natural order to them. You can put them in order. So a very common example of ordinal data are answers on what people commonly call Likert scales. These are these scales that you've came across in questionnaires where you've got to categorize yourself as either strongly disagreeing, neither, agreeing or strongly agreeing with a statement. So that would be considered ordinal, and we'll discuss how we treat ordinal data further in this session. The other type of data you could have is scale data, and that's sometimes called continuous data or sometimes interval or ratio. And that's where you have measurements on a continuous scale, and there's many possible values that you could record. So temperature, for instance, if you're recording that maybe to a decimal place, or weight would be another example of something that's recorded on a continuous scale. So now what I want you to do is identify the type of data in these 5 scenarios. So if we do the first one, the effective surface, I've given you the categories here. So we've got grass, tarmac and track. Because they're categories, then they're considered nominal. There's no natural order to them. For the stride length though, we're taking a tape measure and we're measuring people's stride length. And so that would be in centimetres and it would be considered scale. Again, you can stop the video and have a go at identifying the types of data in the other 4 studies. So here's the answers. We've already done the first one. For the second scenario, we've got colour of museum sign. We can categorise it as dark or white, and so that's nominal. For how long we record people reading the signs, we're recording that in seconds, so we'd end up with scale data in seconds. For recording beer and nappies and whether they're in people's supermarket baskets, I've specified here that we're just going to record whether beer is present in the supermarket basket or it's not present, so whether it's bought or not bought. We're not counting the amount of beer or anything like that. So therefore this is a nominal measure, and we've recorded nappies in the same way, whether they're bought or not bought, so it's both nominal. And it's the same with pet preference. You can categorise somebody's pet preference as cat, dog or both. There's 3 categories this time, so that's nominal. And gender, here we've only got 2 categories, male or female. For the last one, that's a bit more tricky. What we've done is we've measured happiness using these Likert scales type of questionnaire. So this is where we're asking people to agree with statements, i.e. strongly disagree, neither, agree or strongly agree. But we're also using a questionnaire, another feature of the questionnaire, if you like, is that it's multi-item. That means it's got multiple questions to measure someone's happiness. So there's lots of different questions. One might measure, are you happy at work? One might say, you have lots of friends that you socialise with, you're happy with your family. And so there's lots of different questions. And so what we can do with that is we can take the mean of all these questions. So we can consider these Likert scale questions to be ordinal. We're just categorizing them. We're assigning the strongly disagree to strongly agree as 1, 2, 3, 4, 5, but it's still a category. So that's ordinal. As soon as we take the mean, though, we can then argue that we've got scale data. We end up with many possible values once we take the mean. And it's something that's debated in statistics, but treating mean of Likert items as scaled data is quite a common thing to do. For income, we've not asked people for their specific income. We've said that we're going to measure in categories, so we would say 10,000 to 20,000, 20,000 to 30,000. Therefore, it's in categories, but there's an obvious order to those categories. So that's ordinal data. The fourth thing we need to consider is whether our experimental study has pairs, repeats, or whether it's what we call independent data. So let's give you some examples of pairs and repeats so you understand it. Paired or repeated data would be if the people in the study or the samples or the data in the study can somehow be paired, or sometimes it can be grouped in a certain way. And sometimes we measure something or someone more than once. We're doing repeat measures on it. To make that clear, here's the examples. If we were measuring how much weight people lost, but it was a twin study, the twins would be paired. So we would have two values. One would be from one twin, the other would be from another twin, but they would be paired. If we'd been measuring the reading level of 150 children, but we couldn't get all 150 children from the same school, we had to go to 5 different schools, we'd have to be aware that the children are grouped by school, i.e. 30 children come from one school, and then another 30 children come from another school, and so on and so forth. Similar to that, but when we're not talking about people, is if we've taken 20 air pollution measurements, but let's say we only had the equipment to take those air pollution measurements for 3 days. So we had to take all those air pollution measurements over 3 days. The problem with that is that maybe the first 7 measurements would be taken on a Thursday, the second 7 were taken on a Friday, and then the last 6 were taken on the second 7 were taken on a Friday, the last 6 were taken on a Saturday. And maybe pollution levels vary according to the day of the week. So we'd have to be aware that the first 7 are grouped by day, the second 7 are grouped by a different day, and the last 6 are grouped by another day. Another common situation is where we get people to do a pre and then a post test. This would be paired, or sometimes it's called repeated measures. So we have to compare the person's pre-test score with their post-test score. And this would work for rivers, let's say, as well, not if it's not people. If we were sampling rivers, but we were sampling them once a week for 4 weeks, we end up with 4 measures for each river, and we want to compare those measures with the other measures for the same river. So we can think of that as repeated measures. The other thing I'm going to explain to you is the idea of independent data. Now, confusingly, this is completely unrelated to the idea of independent variable in statistics. So you have to be a bit careful with the terminology in statistics. data that can be described as independent is where all the respondents, or the rivers or air pollution measurements, whatever it is you're measuring, they can be considered independent of each other. So they're not paired in any way, there's no repeat measures, or you can't group them in any way that could affect the measurements. That's what we call independent data. So I'm not going to ask you to identify the repeats or the pairs in these 5 scenarios, because all the data in these scenarios are independent. And that's because in the first one, we've got different people running on the 3 surfaces. If we had asked someone to run on grass and then measured their stride length, then the same person to run on tarmac and the same person to run on track, we would have had 3 repeated measurements, and we would want to compare those 3 repeat measurements. We've not done that in this case. We've got 3 different groups of people running on grass, tarmac and track. And just to clarify, in study number 2, it's different people that are looking at the dark and the white signs. So the last thing we need to think about is the number of levels. So if we have a nominal variable, and remember we've already identified the type of data that we've got in our dependent and independent variables. If we've identified it as nominal, we might have to have a think about how many levels it has. And by levels, all I mean is the number of groups. So here, for the effective surface, we've got grass, tarmac, track. 1, 2, 3. That's 3 levels. And there we've written levels. They're just the same as the number of groups. So we've done the first one. You might want to look at the rest of these scenarios and remind yourself which variables are nominal, and then ask yourself how many levels are there. Here's some answers. So we've got this nominal variable, which is the colour of the museum sign, and we've got dark 1, white 2. We've got 2 levels there. For beer and nappy, we're categorising it as either bought or not bought. So that's 1, 2 levels. For pet preference, we've got cat, dog, both 1, 2, 3, and gender, male or female 1, 2. We don't have any nominal variables for the 5th study. That's a thought about our study, and we've clarified the characteristics of our study. So now we're ready to choose the correct test using a flow diagram. So we're going to consider, have we got dependence and independence? And how many independents have we got? We might need to consider. What types of data are those dependents and independents? Have we got paired or repeated measures, or is our data independent data? And how many levels have we got if we've got any nominal variables? So you might want to stop the video and have a go at using that flow diagram to identify this. So you start at the top. The DV stands for dependent variable and the IV stands for independent variable. You can have a go and see what answers you get. If you find that any of them are tricky, don't worry, they're designed to be challenging and to reflect the common situations that we get people coming with into the Mass Skill Centre. So here's some answers. For the first one, we're going to look at the effective surface, which is our independent variable, which has 3 levels and it's nominal, on our stride length, which is a dependent variable, which is scale. So to get the answer ANOVA, this is what we would have done. we would have said, right, we've got a scale dependent variable, so we're going to go to this box as opposed to this box. Then we've got to figure out the number and type of data of our independent variable. We've only got one nominal independent variable, so we're in this box. Now we've got to decide whether our data is independent or whether we've got paired or repeated measures. Our data is independent, and then we've got to look at our IV again, our independent variable again, and see if it's got 2 levels or 3 levels. We've got three levels in this case, the grass, the track and the tarmac, and that's how we end up at one-way ANOVA. Number 2, we've got museum signs, which is nominal with 2 levels, and it's an independent. And then we've got this reading time in seconds, which is our dependent, which is a scaled variable. So we've got this dependent variable scale. So we're going to again start in this box. Then again, we've got only one independent variable, and it's not scale, it's nominal, so we go to this box. Again, we don't have any pairs or repeats, our data is independent, so we go to this box. This time though, that independent variable, which is, remember, our museum signs, it only has 2 levels, so black or white, sorry, dark or light. And so we end up at independent samples t-test. For the third one, we've decided that we didn't have any independent or dependent variables. And we've decided this is nominal and this is nominal. So to get the correct answer, what we would do is we'd go to this box here, because this says there's no dependent variables or independent variables, i.e. we're just testing for an association. We've only got one option here, which is where we've got 2 variables. And then we've got to look at the type of data that we've got. So we've got a choice here where both types are scale, both are ordinal, or one's scale and one's ordinal, or both are nominal. We're going to go to both variables be nominal, because we can categorize them as either being bought or not bought, and that's how we end up down at chi-squared. The next one you might have found difficult, and that was intentional, because it is difficult deciding this scenario, but it's a really common study design that we see quite often. So here we do have a dependent and an independent variable. And so the test that we would use for that is something that's not commonly used. It's a bit of a tricky test. It's called log linear, but it's quite an advanced statistical test, and a lot of people aren't familiar with it, and it's hard to interpret. So what happens is people resort to using chi-squared, and it's quite common to accept a chi-squared to do in this case. The reason that chi-squared isn't the best test to do is because chi-squared only tests for an association between these 2 variables. And actually in this case, we've got a dependent and independent, we've got a cause and effect. We're hypothesizing that gender causes an effect in the pet preference. Nevertheless, we would use the chi-squared. So just to reiterate the problem here, the 2 variables we've got one dependent and one independent, but they're both nominal. So we can't choose this box and we can't choose this box. So if you find yourself in that scenario, just consider whether you've got a scenario that's like this situation, where you've got a nominal and you're looking for cause and effect. In that case, do chi-squared. For the 5th one, again, This is tricky because it depends on how you're hypothesizing the research question. So are you hypothesizing that you're testing an association between happiness and income? Or are you saying that there's a cause and effect, so income causes happiness to change? Let's say, first of all, that you're thinking about just an association. So there's no dependent and independent variable here. In that case, we would go to the flow diagram and we would go to this box. There's no dependent variable or independent variable. We're just testing for an association. We've got two variables, income and happiness. The variables aren't nominal, and the variables aren't scale either. We've got one scale, which is the mean of this multi-item Likert scale, which measures happiness. And we've got one ordinal, which is the income. So I'm going to go to a Spearman's rank correlation in that case. However, if we were hypothesizing that there's a cause and effect, now we've got a dependent variable, which is the happiness, and an independent variable, which is the income. And this is where it gets slightly tricky. We start off with our dependent variable being a scale dependent variable. So we're in this box. We've got one independent variable, so we're looking at either this box or this box. Now this box says that the independent variable is nominal, and that's not true in this case. We've got income categories, but they're not nominal. This box is saying that we've got one independent variable, but it's scale. Again, that's not strictly true because we've got an ordinal independent variable. But what we're going to do is something that's really commonly done. We're going to treat that ordinal scale as scale data. So some people will disagree with this. If you're very strict about statistics, you might not want to do this. And if you look at some guides that tell you how to do this simple linear regression test, they'll say that an assumption is the independent variable is a scale data. So I'm sort of saying that it could be considered a grey area. In some disciplines, it'll be routinely done and people won't bat an eyelid at doing it. So if you're in that scenario, simple linear regression would be the correct test to do. So now we've decided what test we're doing. We're ready to test some assumptions, and I'm going to explain what an assumption is. You can think of assumptions as criteria that you've got to meet in order for a statistical test to give you a sensible answer or a reliable answer. So people have designed these statistical tests, but when they've designed them, they've realized that they only work under certain conditions. So they only work when your data is in a certain way, when your data meets these criteria, i.e. your data meets the assumptions of the test. Assumptions are different depending on the statistical test that you want to use. So for example, if we wanted to use an independent t-test, some of the assumptions, and they vary between what textbooks you look at, would be normal distribution of the data, or something that we call normality. It would be equal variance, and some people call this homogeneity of their variance. And both of these assumptions can be tested in SPSS, so you have to use SPSS to test them. Another assumption is that you've got continuous data for your dependent variable. So that's the same as scale data. And so we're just looking at the experiment. You should be able to identify that. Another assumption is that you've got independent data, i.e. there's no repeats or no pairs. Another assumption is that there's only two levels for the independent variable, i.e. in our museum science example, we've only got light and dark backgrounds for museum science, so that's 2 levels. And we also don't want any outliers, and we can look at that in SPSS as well. So I'm going to teach you how to test for these 2 assumptions and try to explain what these assumptions are. I'm also going to teach you how to test for another assumption which is quite common for tests for correlation or linear regression. And that assumption is something called linearity. It's just seeing if your data falls in a line, in a straight line. So first of all, let's check for normality. So this is testing for a normal distribution. If you joined us for getting started with SPSS, it might look familiar. And that's because it's a recap from that session. I went through how to test it in SPSS in that session, but I didn't necessarily explain it. So to do that, we need some data. This is pretend data. You can find it on the Math Skills Centre VLE where you found this video. And the data I want you to open up is called Workshop Data Museum Signs. So if we go there, Workshop Data is here. We click on Museum Signs. Your SPSS might take longer to open up, and that's absolutely fine. So there's instructions here on how to test for normality. And what we're going to do is we're going to run one test to test if the sign color for the light sign color is normally distributed, and we're going to run another test which looks at the dark sign color. So we're actually running 2 tests. The test we're going to look at is something called Shapiro-Wilk. It's just named after the mathematicians who invented it. A Shapiro-Wilk test is probably the most common test that's used among SPSS users, but there are other tests that will do the same thing. So we'll run the test and then I'll explain it. If we go to Analyze Descriptive Statistics and Explore, we're going to put our dependent variable gaze in time under the dependent list and our sign color under the factor list. Then we're going to click Plots, and if we click this box here, if we tick this box here next to histogram, we're going to get a graph. We're going to get 2 graphs in fact. And if we tick this box here, normality plots with tests, it's going to run 2 Shapiro-Wilk tests for us, which will give us the answer, and it will tell us whether we've got normal distribution or not. Click Continue and OK, and we'll get an output window popping up. So there's the data there. Don't worry if it takes a long time to come up. You can see here that we've got some descriptive statistics for the light background and the dark background. So we've got a mean, median and standard deviation, standard error here. The things that we're interested in terms of looking at normality are this box here and these 2 diagrams here, these 2 histograms down here. So what this Shapiro-Wilk test has done is it's taken let's say it's taken a histogram, if you like, of our data. So it's plotted our data like this, but in a computer way. And then it's taken a perfect, symmetrical, theoretical bell-shaped curve. So it's created a bell-shaped curve, and it's done a test to say whether there's a difference between our data and this theoretical perfect bell-shaped curve. Now we want our data to be this nice normal distribution bell-shaped curve because that's the assumption of the test. So we want our data to be the same as that bell-shaped curve. So the way you interpret the test is by looking at the p-value. Now the p-value is given under the sig box in this table here. The way to interpret this test, and if you're new to statistics you might want to write this down, is this. If the p-value for Shapiro-Wilk is less than 0.05, then there is a difference between your data and the perfect theoretical normal distribution. That means your data does not meet the assumption of normal distribution. So here we can see the light background is less than 0.05. The light background is not normally distributed. If the p-value is greater than 0.05, that means that there was no difference between our data and a theoretical bell-shaped curve normal distribution. And therefore our data is roughly a normal distribution and it meets that assumption of normal distribution. So you can see here the dark background is above 0.05. So the dark background data does meet the assumption of normal distribution. So we've got one half of our data doesn't meet it, one half does. The other thing I recommend you do is look at the histograms, because that gives you an idea of what's going on. And if we look at the light background, we can see why the test found that it didn't think it was normally distributed. It skewed at the right. We've got a quite high value here. Whereas the dark background is more of a normal distribution. This is where judgment and your experience comes in, because you might think that doesn't really look like a smooth bell-shaped curve. But that would roughly be okay. I would pretty much accept that. The only other thing I'm going to talk about in this output are these box plots we've got here. Box plots are good because they show us outliers. So here you can see the light background has this outlier, and you can decide to do different things with outliers. It might be okay to exclude data, but you might not want to throw away that data. You might want to run the test with and without the outlier to see how it affects it. I'm going to talk about something called transformations and explain what they are. However, they could be considered to be going out of fashion. Some people don't like using them. They don't think they work. So again, you've got to look at your discipline and see if transformations are a common thing that are used. Transformations can be useful because if your data is not normally distributed, what you can do is try and transform each point. Transform is when you put the data onto a different scale, such as a logarithmic or log scale. So we use this scale of 1, 2, 3, 4, 5 every day. We're familiar with that scale. But what you can do is put it into a different scale. I sometimes explain this as it's like putting your data into a parallel universe. It's the same data, it's just on a different scale. So I'll teach you how to do this, but bear in mind you might not want to implement this technique. So let's say for our museum data, we've got this light variable that doesn't meet the assumption of normal distribution. So we're going to try to transform it onto a log scale, then test it again for normality to see if it meets that assumption. So to do that, we go to transform and compute variable. We're going to we're going to create a new variable, so a new column. So we need to tell SPSS what we want to name that column. I'm just going to call it log gazing. And then I'm going to choose the function log from this list. So it's LG10. And it gives you explanation there. If we double click it, it'll jump up there. And it's asking us, what do you want us to take the log of? Well, we want it to take the log of this variable here, this scale data, gazing time here. When we click OK, we'll get rid of our output window and go back to our data view. You can see there it's taken each of the gazing time values and put it onto a log scale there. So now what we're going to do is we're going to test that data for normal distribution. So I'm going to use my recall button to go back to Explore. I'm going to replace the normal data on the normal scale with the log data. I'll just check that I've got my histogram ticked, yep, and my normality plot with test box ticked, yep, I've got that done. And now I've got the same output, but it's for the transformed data. So looking back at my Shapiro-Wilk tests again, the Shapiro-Wilk test for light background, it's saying that it's normally distributed, i.e. there's no difference between my data and a theoretical bell-shaped normal distribution. And same with dark background. Again, there's no difference because the p-value is greater than 0.05. So I've got normal distribution for both of them. And if I just check my graphs, you can see here I've got a graph. It's still got a bit of a skew. It's not great, so I might not want to use the independent t-test. But this one's quite nice. This one's quite nice and normally distributed. I better just check my outliers again. You can see I've got rid of the outlier in light background, but there's another one appeared in dark background, so I might want to consider removing that or running the test with and without it to see the effect of it. So that's us tested for normal distribution. Another assumption, which is common and which is an assumption of the independent t-test, is something called equivariance. And I explain variance as the variation in the data. You can think of it as the spread of the data. If all the data points in, let's say, the light background data are very, very variable, let's say they're between 5 seconds and 100 seconds, whereas the data points for the dark background were all between 40 and 50 seconds, it's very unlikely that the variance in those two data sets would be equal. So in SPSS, a Levene's test, which tests for equivariance, is run at the same time as a t-test. So you don't have to run a separate test, you don't have to tick an extra box or anything, it just automatically does it. And what you need to do is you use the result of the Levene's test and decide which version of the t-test output to use. So if you don't meet the assumption of equivariance, you can still use an independent t-test, but you just have to use a different output. So if we ran an independent t-test in SPSS, we get this output here. Now, the results for the t-test are in this section of the table. The results for this Levene's test, which tests the assumption of equivariance, are here. So we'd look at the p-value for the Levene's test, which is this number here. If the p-value is greater than 0.05, there's no difference between the light and dark variance. And therefore, we would use the results from the top line of the independent samples t-test. But if, like in this case, that p-value from the Levene's test is less than 0.05, that can be interpreted as there being a difference between the variances of the light and the dark background, i.e. we don't have equal variance. In that case, we're going to use this bottom line where it says equal variance not assumed, and we'd use this line. of results for our t-test. So that's all the assumptions for an independent t-test. I did say that I was going to teach you how to test for another common assumption, and that's for linearity. So this is an assumption which is common for correlations or for linear regressions. And all it is you plot your data and you're looking to see whether it looks roughly like a straight line. And what you don't want is there to be something else going on, so a different shape of line, a curve basically. So here we've got some examples from 4 different studies. The first study, we've plotted the data against each other, and you can see that it's quite variable, it's quite scattered, but I would consider that as linear. Again, the second one we've plotted, this time we've put in a line of best fit, and you can see I'd consider that linear. It's roughly in a straight line. What wouldn't be linear is if it goes up and then down, or if it goes up and plateaus off. We can't put that into a correlation or a linear regression. It violates the assumption of linearity. And here, this is an interesting data set because we've got data that looks very, very scattered. If we put a line of best fit in it, we can actually see that there's a curve to it. We don't want to put that into a correlation or a linear regression. It's violating the assumption. We wouldn't get a reliable answer. So let's test for linearity, but we're going to use a different data set. We're going to look at this study where we're looking at the effect of income on happiness, or we're looking at the association between income and happiness. So go to the VLE and open up the workshop data happiness. We're going to use the chart builder in SPSS. So go to graphs, chart builder, and we can choose the type of graph we want. We want a scatter dot plot, and we're just going to use this one here. This is a simple scatter. We click and drag it up to our chart building area, and then we're going to put overall happiness. So that would be where we've taken the mean of 4 items. We're going to drag that to the y-axis. Doesn't really matter what we put on there because we're just demonstrating how to get linearity. And then we're going to put our income on the x-axis. We'll click OK, and in our output window, we'll get a graph. And you can see there's a lot of variation here. It's quite messy. But I would consider that that's okay to put into a correlation or a linear regression. That's acceptable. So you do need to use a bit of judgment. So the reason we've been testing these assumptions is because there's a set of statistical tests which have assumptions, and we can describe them as parametric tests. And we want to use parametric tests if possible. They're more robust. What we call in statistics as being more robust tests if we meet the assumptions. However, if we violate the assumptions, so we don't meet the assumptions, i.e. maybe our data is not normally distributed, we might have to use a non-parametric equivalent. So if we think we want to use an independent t-test, so our data is suitable for an independent t-test, but we're violating the assumptions, we could resort to its non-parametric equivalent, which in this case is a Mann-Whitney U. Another example of a parametric test is a Pearson's correlation. But if we didn't meet the assumption of normal distribution, or maybe of scale data, we might have to resort to Spearman's rank correlation, which would be the non-parametric equivalent. So if you hear people talk about these terms, parametric and non-parametric, we're talking about different types of tests and whether they have strict assumptions or not. So this section we're going to run through some statistical tests in SPSS. But the idea is not to teach you how to run a specific statistical test, rather where you can find help for running the test that you need. So I'm going to run through 3 tests and use different resources to run each of those tests. The first test we'll do is an independent t-test. That's the test we need to analyse our museum signs data that we've already got open in SPSS. The hypothesis we're going to test is that there's no difference in the time spent gazing between the 2 colours of museum signs. And if you remember, we've already checked the assumption of normality using those 2 Shapiro-Wilk tests and looking at the histogram. We've also looked at the equal variance test, the Levine's test. So for this, I'm going to use an online resource called Laird. If you wanted to get a Laird guide on a specific test, you could type into Google Laird independent t-test. I've got a link here for the test we're going to do. And this guide reminds us of assumptions. It tells us what menus to go to and options to choose, but also how to interpret the output, which is really useful. So this is the Laird guide here. The introduction, assumptions, explains what example data they're going to use. And then we've got the test procedure here. So you can see they've got really clear screenshots here. So let's go to our museum signs data. And to do an independent t-test on it, we go to Analyze, Compare Means, Independent Samples t-test. If we scroll down on our Laird guide, it tells us to put in the dependent variable. Now we're going to use our transformed data because that meets the assumption of normal distribution. Put the dependent variable under test variable, then put the independent under the grouping variable. Then it says you've got to click on the define groups. In the Laird example, they've used 1 and 2 to code up their treatment groups. In our example, you can see here we've got zeros. That's because we coded ours as 0 and 1. So we're going to put 0 and 1 in there. And that's just so SPSS knows what groups to compare. Sometimes you have more than 2 groups. It has an option here to change the confidence interval, but we're not going to do that. So now we click on OK. And in the output, we looked earlier at the result of the Levine's test. So the p-value is less than 0.05, which means we don't have equal variance. So we're going to look at this bottom line of results. Now the main thing that we want to look at is the p-value here. It's under this sig2 tail. And because the p-value is less than 0.05, then we know that there is a statistically significant difference. So that means that there's a difference in the gazing time between people that were looking at light background signs and dark background signs. In the Laird guide, they walk you through the output. There'll be other values that you need to pick out. And then they give you an example here. So you can't just copy and paste that table into your report. You need to put it into sentences with the results that look a bit like this. So that's one resource you can use. Another resource is the Stats Tutor website. So we're going to do a chi-squared just to demonstrate the videos on the Stats Tutor website, and we're going to use the data workshop data cats and dogs, which is on the VLE. So if I go to the VLE and open that up, it's under here. And we've just got people's gender and whether they prefer cats, dogs, or both. And you can see in the variable view what those codes mean. So one's female and two's male, and one is cats, two's dog, and three means that they prefer both. So we're going to test the assumption there is no association between gender and pet preference. And I'm emphasizing the word association here because remember, this might not be the most ideal test to test this hypothesis, because actually we were thinking that gender would have an effect on pet preference rather than that there's just an association. So just be aware that if you're using chi-squared in a similar situation. We could go to the Statistical website, click on video tutorials, and choose chi-squared test using SPSS. So let's do that. Click on video tutorials. There's other resources here that you might find useful. Click on the video, and if we play that, it has data, and it'll run through how you run the chi-squared. You can watch that in your own time. If you just watch the first minute and 30 seconds, it'll tell you to click on Analyze, Descriptive Statistics and Crosstabs, put one of your variables under rows and the other under columns, click on cells and tick the expected box, then click on Statistics and tick the chi-squared and Phi and Kramer's V. When we click OK, we get the results here. So these are just three very similar ways of running a chi-squared, three ways that different people have came up with. The thing we're interested in most is the p-value again. So again, it's not under p-value, it's asymptotic significance two-sided. So because these p-values are greater than 0.05, we can interpret that as there being no statistically significant association between gender and pet preference. The next test we're going to run is a Spearman's rank correlation. This time I'm going to talk about using books. So we're going to use the happiness data that we already have open in SPSS to test the hypothesis that there's no correlation between happiness and income. So we've taken the view that there's no cause and effect. We just want to test for an association. You could use a book called SPSS Survival Manual. It's by Julie Palant. There's a 6th edition out now, and it's quite straight to the point when it's trying to explain how to run these tests in SPSS, so you might like it for that reason. So Palant's book would tell us, if we go to the data, the happiness data, let's find it. Here we go. It tells us to go to Analyze, Correlate and Bivariate. The two variables that we're comparing are income and the overall happiness, which remember is this mean of the 4 questions, mean of the 4 items. We tick the Spearman's box, and then it recommends clicking the options and saying leaving the default excludes cases pairwise. And you might want to click means and standard deviation. It's not going to let us click means and standard deviation in this case. And that's because we've got this variable in as an ordinal variable. We'd have to change that income variable to scale in order to get this to work. If we click OK, in the output window, we get this grid. Now just be aware that it repeats the results. So the results are here, and we want the sig2 tail as our p-value. So our p-value is 0.015. It's less than 0.05. That means that there is some sort of association between happiness and income. And you'll see that that's repeated down here. So these 3 numbers are repeated down there. It's just the way that SPSS displays it. your R value or correlation coefficient is up there as well. You'll want to report that in correlation. But Julie Palin's book will explain how to report it. The final resource that I want to talk to you about is a book by Andy Field. It's a very popular book among SPSS users. The University of York Library has about 40 copies. And it's a bit more of a light-hearted look at statistics. He includes little jokes and things like that. So if you want to practice all that, you can do the exercises. These exercises take real data that we've harvested from the internet to show you that statistics can be useful in answering real questions. So if you want to find out why no one wants to marry York residents living in Heslington opposed to Acomb, you might be interested in that, being a student living in Heslington. You can look at the census data we've pulled out. You might want to look at the association between sweets, chocolates and ice cream consumption for our country and how happy that country is. Or if you want to think about how much you're going to earn in the future as a University of York student opposed to a student living in London, you might want to look at the data we've got on that for you. The exercises are on the VLE. There's also a solutions sheet on the VLE for you as well if you want to check your answers.